Namaste everyone. Welcome to class 11, chapter 4, Mathematical Induction, module 1. Today we shall cover introduction of deduction and induction method, understanding mathematical induction by illustration and the principle of mathematical induction and few examples. Now, what is mathematical induction? Mathematical induction is nothing but a mathematical tool or a technique to prove mathematical statements. Like we use different tools for different purposes. Same way in mathematics also we use different methods for different type of problems, and mathematical induction is one of them. And before explaining mathematical induction, there is another technique also, mathematical deduction. So let us first understand what is deduction. Thus, deduction is a given statement to be proven, often called conjecture or the theorem. Theorem name already know. Valid deductive steps are derived and proof may or may not be established in theorem. Like you did in many theorems in earlier classes, we do it by method of contradiction. So, deduction is an application of general case to particular case or a specific case. Let us understand with the help of example. Like Pythagoras is a man, all men are mortal. So, we can conclude that Pythagoras is mortal. Basis on these two statements, we can deduce the statement that Pythagoras is mortal. Let us take another mathematical example. Let 6 is divisible by 2 and any number divisible by 2 is known as even number. Therefore, 6 is an even number. So, we conclude this or deduce this result depending upon above two statements or above statements. So, this is the case from general to specific. These are general statements, we are coming to specific. Now, inductive reasoning depends upon working with each and every case and developing a conjecture by observing incidences till we have observed each and every case. Let us understand with the help of one example. Suppose Reena eats food, Meena eats food, Veena eats food, Deepak eats food, Aman eats food. And if we say Reena, Meena, Deepak, Aman, all these are humans. So, we can generalize from this result that humans eat food. So, we are moving from specific to general, like, and this inductive method is frequently used in mathematics and it is a key aspect of scientific reasoning. It is logical reasoning where collecting and analyzing data is a norm. Thus, in simple language, induction is from specific or particular cases to generalization. Now, with the help of this mathematical example, you can understand it better. 1 is an odd number which can be represented 0 plus 1. 3 is an odd number which can be written like 2 plus 1, where 0 and 2 are even numbers. Now, 1 plus 3 is 4 and 4 is an even number. Now, we can write this odd number which is equal to even number plus 1. This is odd number, even number plus 1. 3 is odd number, even number plus 1. Now, from above these statements, what we can generalize is that two odd numbers are actually two even numbers plus 2. And this is the mathematical example. So, in algebra or any other discipline of mathematics, there are certain results or statements that are expressed in terms of n, where n is a positive integer. For example, if I ask you to add natural numbers till 50, like 1 plus 2 plus 3 plus 4 till 50, you can do it, though it is a lengthy process, but if I ask you to do it like 1 to 50,000, then you will not be able to do it. If I give you a formula, then it becomes easy for you. Now, formula means that will be expressed in terms of n. There are many formulas. To prove such statements or well-suited principle that is used based on specific technique, and it is known as principle of mathematical induction. And before moving to mathematical induction properly, I would like to take one interesting example, that is dominoes effect. On internet also you must have seen many pictures or gifs or videos where rectangular tiles are placed at some particular distance, and if we push one of the tile, other next tile will fall, that will make the next tile will fall, and likewise all the tiles will keep on falling till end. So let us understand with the help of one video. As you can see in this video, if we have pushed one tile and it is making the other tiles fall, and the all tiles keep on falling, and with the help of this picture you can see here this man is pushing this tile and this tile is making the other tile fall, and so on. Can see? So when we first tile is pushed in the indicated direction, all tiles will fall. To be absolutely sure that tiles will fall, it is sufficient to know. Means suppose we have pushed one tile and we move to other side without noticing whether first tile has fallen or not. If first tile itself has not fallen, how the other tiles will fall? No question of it. So we need to ensure when we push first tile, it should fall. If it falls, then how it impacts the other tiles. So it is sufficient to know that first tile falls. We need to ensure that. The second step is in the event that any tile falls. Any tiles means if we pick any random tile from it and if we find that that tile falls, we need to check whether subsequent or the next tile falls or not. These are two major steps to be taken care of while studying mathematical induction. So this is the underlying principle of mathematical induction, beautifully explained with the help of domino effect. And with this domino effect, in this present scenario of COVID-19, we can easily explain the social distancing with these pictures. Like this is the coronavirus and it has pushed one tile or the people it has attacked and it is spreading like anything. But if we create a distance between these tiles, that much sufficient distance that if one tile falls, it does not affect the other tile, then these tiles will keep standing, they will not fall. So by following this principle of social distancing, we can help to stop or slow down the spread of coronavirus. Now mathematically, principle of mathematical induction. Formula is a mathematical statement and we use mathematical induction to prove these statements, and the sum of first n natural number is given by this formula. We need to prove this formula. Why we need to prove? You may say that if we put n is equal to 1 means we want to find out sum of first natural number or one natural number. If we substitute n by 10, we can prove it both way by manually doing the sum from 1 to 10, and by substituting in the formula we can easily prove it. But we cannot prove it for bigger terms. If I substitute it for 50,000, I can find out the value by this formula, but manually if I want to do it, it is very difficult. Still if I do it, but I want to prove it for further bigger number, this is difficult. So we need some tool or technique that helps us to prove these formula, and that is nothing but mathematical induction. So principle of mathematical induction, we need to follow these steps. First we need to give the name to the statement. There is a given statement Pn involving the natural number n, where n represents a natural number. The first step is the statement is true for n is equal to 1. We need to prove that it is that I have told you in the case of tiles, domino tiles, that first tile need to be pushed and it should fall. Then only we can move further. The same here for any formula, we need to prove it for 1. This is the basic step. Next step is if the statement is true for we have assumed that it is true for P1, we have proved it. Now it is statement is true for n is equal to k, where k is some positive integer. As I told you in case of dominoes, that if we pick at random any tile, if it falls, I am stressing it because we assume that any random tile falls or any random number k. The formula is true for any random number k, then we need to prove that its successive number, that is k plus 1, it is true for n is equal to k plus 1 also. And if it is true for k plus 1, then we can say that formula is valid, or truth of pk implies the truth of k plus 1. So, Pn is true for all natural number if this is true. Now, let us understand it with the help of example. Now, before moving to the mathematical example, we would like to highlight few properties that we explained in principle of mathematical induction. The first one was basic step that we proved for 1, but it is not always true for all the formulas, because it is simply a statement of fact. There may be the situations when statement is true for n greater than equal to 4. What do we mean by greater than equal to 4? Here first step is not n is equal to 1. Here we will be taking first step as n is equal to 4 instead of 1. So, we will write P4. The first step we will prove as P4 should be true. Now, the second property, that was our inductive property, it is a conditional property. It does not assert that given statement is true for n is equal to k, because here we assume that. Here we assume if at any random number taken from that series of formula is true for k, then only we move further to prove that it is true for n is equal to k plus 1. So, you need to take care that we prove it for, we assume it for n is equal to k. Assume word is important here. So, if the statement is true for n is equal to k, here if is an important word, then it is also true for n is equal to k plus 1. So, this is inductive hypothesis. First one was basic step, this is inductive. The assumption that given statement is true for n is equal to k in this inductive step is called inductive hypothesis. Now, observe this pattern where this 1, it is an odd number. Odd number can be represented as square of first natural number. Sum of two odd numbers 1 and 3 can be represented by square of second natural number. Sum of 3 odd numbers can be represented by square of third natural number, and sum of 4 odd natural numbers can be represented by fourth, because they are 4, therefore fourth natural numbers square. And similarly, we can go ahead. From this pattern, you notice that is 1 plus 3 plus 5 plus 7, 2n plus 1 represents any odd natural number, and this is equal to n square. So, sum of first and odd natural numbers is square of n. Let us write this statement as Pn first. This is the first step of using principle of mathematical induction. Now, Pn is a statement which needs to be proven, that is sum of n odd numbers is equal to n square. We wish to prove that Pn is true for all n. It is true for 1. How it is true for 1? We are saying obviously, because if we substitute 1 here, this is 2 minus 1. On the left hand side it will give us 1. On the right hand side also it will give us 1. So, we can easily say that P1 is true. That is why it is called basic step. Assume, again I am stressing, assume that Pk is true for some positive integer k. We need to prove it for Pk plus 1 is also true. For that, first we write, since we are taken that Pk is true, we can easily replace here n by k. So, this is the statement 1, we name it. Now, consider the statement for k plus 1, Pk plus 1. Means we need to replace here n by k plus 1. If I write here 2 k plus 1 minus 1, this is the last number of this sequence. What will be the previous number? Previous number will be obviously 2k minus 1, and this is for k plus 1. So, we have replaced it with this. This is up till k terms, and this is our k plus 1th term on the both side. Now, we know that this much result from the statement above that this is equal to k square. I have replaced this whole term by k square and adding the k plus 1th term to this. After solving this, 2k plus 2 minus 1, it will give us 2k plus 1, and on the right hand side, in place of k square, we need to write this. Means we need to show that this left hand side is equal to right hand side. Now, as you know that this is the term here, we are left with 2k plus 1. If we combine this, this makes the formula for k plus 1 whole square. This is nothing but k plus 1 whole square, and this is what we wanted on the right hand side, because for k terms it was required k square on the right hand side, and for k plus 1 terms we can write k plus 1 whole square, and that's it. Now another example, for n greater than or equal to 0, we need to prove that sum of squares of natural numbers is equal to n into n plus 1 into 2n plus 1 divided by 6. We already know this formula and we have been using it, but how we can verify it? By mathematical induction. First step, basic step, that is for n is equal to 1, because here our first term is 1. So P1 is nothing but, if we solve it, replace here n by 1, this will give us 1 into 2 into 3 divided by 6, which is 1. So our basic step is true. We can move further. Let us assume that it is Pk is true for some positive number k. Now since we have assumed that Pk is true, we can easily replace n by k here. So 1 square plus 2 square plus 3 square plus 4 square till k square gives us k into k plus 1 into 2k plus 1 divided by 6. We assume that it is true, therefore we give it a name as statement 1. We shall now prove that the statement Pn is true for n is equal to k plus 1 also. So for k plus 1, what we need to do is, we will write the terms till k and then the next term, which is k plus 1 whole square. Taking another extra term, if we take extra term, this sum will come, adding to it the square of the next term. Now we need to show this, and taking left hand side, we know that up till this term, up till this, we already know this is equal to this. We replace this by this result, and we are adding this 6 denominator will multiplied by this will give this result. After solving this expression, we get k plus 1 into 2k square plus 7k plus 6, and factorizing this quadratic equation, we have factorized it, you can see here, and we see that all the terms in terms of k plus 1. So if we compare it with k, and this is k plus 1 and this is nothing but 2k plus 1. If we compare it, since it was true for k, now it is true for k plus 1, k plus 1 plus 1, 2k plus 1 plus 1 divided by 6. So we can see that this statement Pn is true for Pk plus 1 also. Thus Pk1 is true whenever Pk is true. Hence, from principle of mathematical induction, Pn is true for all n, that is where n are natural numbers. Today's module 1, we covered introduction of deduction and induction method, understanding mathematical induction by illustration, and principle of mathematical induction, basic step and inductive step. That's all. Thank you.